Oh, okay. I'll just do an intro. Well, hi everyone. So this project is by Aman and me, and we decided to work on MRI reconstruction, which is like a new sort of theme that has been happening in like medical imaging. And essentially, the gist of it is that typical MRI images can take more than an hour to scan, and so we can accelerate this process using deep learning. But in doing so, we sacrifice accuracy for time of scan, and so essentially, what we're doing is we're reconstructing um, the lower quality MR images into high quality MR images with a generative adversarial network, or GAN. So we're just going to go into our project and explain how we did it this semester.
Yep, so just a bit of an agenda for today. We're going to start off by just talking about the motive and the background, and then getting into our data set, and then talking about implementing the GAN, and then moving on to the results and analysis, and then some next steps and the contributions that we brought to the project.
Mm-hmm. So just going into the background, I don't know if I already showed you guys this video, but do you guys want to watch this video? It sort of inspired us to do the project.
I don't think I've seen it.
Okay. It's only like 2 minutes, or like 1 minute 49. Can you hear it?
No.
I don't think so.
Oh, the sound doesn't.
Yeah, how do I? Oh shoot! Wait, where's Teams? Okay.
Yeah, make sure it's set to share computer audio too.
There's a way. I remember I did this last time.
Yeah, you can unshare your screen and then share it again. When you share it again, the dialog asks you if you want to share the system's audio.
Okay, I think I got it. Let's go back. Let's go here. All right, let me know if you can hear it.
Yeah.
Okay, cool.
When a patient is scanned for an MRI, high-powered magnets and radio waves gather raw data to create images of their anatomy. But capturing all this data can take up to an hour, which can be difficult or impossible for some patients who can't stay still like small children. Long scan times also limit how many patients can be evaluated in a day, especially in places with limited MRI access. It also means that MRIs could be too slow for emergency situations like strokes, where doctors need images quickly.
With Fast MRI, NYU Langone and Facebook AI are using artificial intelligence to make MRI scans much faster. To do this, we created the largest open-source de-identified MRI dataset and used it to train a deep neural network. This enables our AI to generate accurate images from far less data. Since less data is needed, scans can be much faster.
We've now completed the first major test for Fast MRI. In a rigorous clinical study, radiologists found AI-generated images created with 4 times less data were diagnostically interchangeable with traditional MRIs. Additional testing is currently underway, but the study shows that with AI, we can significantly improve the patient experience and provide the benefits of MRIs to many more people. And we believe this open collaboration between AI researchers and medical imaging experts can serve as a model for future breakthroughs.
All right.
Cool.
Yeah.
Cool, yeah. So that video was just kind of showing how we got the inspiration for the project. So now let me just talk about some MRI basics. So an MRI is pretty much just a big magnet. That's really what it is. So the unit of measure of these magnets is in the unit of a Tesla. And just to put into perspective what the Tesla unit, like how strong it is. So most MRI scanners have magnets with strengths between 1.5 to 3 Tesla. And that's actually 60,000 times stronger than Earth's magnetic field, which is only like 0.003 Tesla. So these are really, really strong big magnets that are in the MRIs. So in terms of how it works, our bodies have hydrogen atoms because we're made up of 65% water. So these atoms are spinning in random directions, going all over the place. And when we put our bodies into the MRI machine, the magnetic field that the MRI is generating is going to make these atoms align. So some of them will align in a parallel direction, and they'll be facing upwards, and then the others will be aligning in the opposite direction, facing downwards. And due to laws of quantum physics that are out of the scope, there are going to be more atoms that are aligned up than down. And the total magnetic field that's generated by these hydrogen atoms is quite small because most of the upward aligned protons canceled with the downward aligned protons. But there's still some extra upward aligned ones. And that's the net magnetic field that's generated. So that net magnetic field is what the MRI captures to produce the images. So after applying this magnetic field, there's a radio frequency pulse that's emitted at the same frequency, creating resonance with these spinning protons. And that's where resonance comes into the MRI. And then essentially once that radioactive pulse is turned off, the protons are going to realign to the normal magnetic field, and whatever energy is released during that process is captured by the coils of the MRI, and that's what creates this K-space that you can see in the visual. And then some mathematical transformations are applied to this K-space to produce the images that doctors see. So, yeah.
Yeah, that was a pretty good explanation. A bit complicated, but essentially in this project, we didn't really need to focus on all the particle stuff. We just focused on the K-space and the actual image construction. So don't worry if you didn't understand that. I guess here's like an animation to just show exactly what Aman was talking about. You can sort of see this is like the magnetic field, and all these arrows correspond to the direction of the water molecules that he was talking about. And this is what happens when the MRI machine is on. And it basically uses its magnetic ability to like reposition the direction of all these water molecules. And then as soon as you turn it off, the water molecules go into their normal directions, and that sort of release in energy is what we're measuring in the K-space.
So when we're going from the K-space to the actual image, as I mentioned, there's some math transformations that allow the actual image to be created. And that's actually through this transformation called the Fourier transformation. And this is pretty much the basis of how we construct our data set that we're going to get into. But essentially a Fourier transformation breaks down any kind of a signal into sums of sine waves. And then those individual components that when added create the image are what the K-space is. So the K-space is the individual components, and when you sum them up, it produces the image on the right. So the Fourier transformation goes from K-space to image.
Yeah. And now just going into the data for training our GAN, we decided to use the MRNet, which is quite a popular data set for MRI images in machine learning. Yeah, I think this is from Stanford Medical Center, and some of the knee images that were in the Facebook AI video are MRNet images. So this is kind of like a standard.
Yeah, so now getting into the pre-processing, most of our images were given to us in this nii.gz format, and we had no clue what that was because we're not doctors, but after doing some research, we learned that the NII files are, they're in this format called the NIfty format, which is a convention for neuroimaging that doctors use. And then GZ is just, it stands for gzip, so it's compressing these NII files. So pretty much we unzip them with the gzip library and then process these images using NI-Babel, which is in Python. And the NII files are in 3D volumes. So we had to pre-process them so that we could extract 2D slices, because that's what we used in our training data. And then there were some images that had a lot of 0 pixels, and they were pretty much just useless images because there were so many 0 pixels. So we set a threshold and said, okay, if we have more than 15% zero pixels in out of all our pixels, then let's just drop this image. We don't even need it as in our training data. So that was one condition. And then now let's talk about how we actually created our training data and the undersampled images. So essentially, we took the image, conducted a Fourier transformation, which broke it down into its k-space. And then in the k-space, we multiplied the k-space by a mask. And this mask essentially just highlights the most prominent features in the MRI image. So the mask, as you can see in this PowerPoint slide on that bottom picture, that's how the mask looks like. So if we multiply this by the k-space, that's going to give us an undersampled image. And then on top of that, we add some noise to it. And then we conduct an inverse Fourier transformation to go back to the image that we typically see as the consumer. So that's how we did the undersampling. And then finally, we stored our data in pickles just to make it easy to reproduce and train with.
Yeah, yeah, that was pretty good. One thing I just wanted to add, sort of like in the research process, before understanding like MRIs and how they worked, we just thought the data set was, we could just undersample the actual resulting MRI image by just like lowering the quality of it to create our data set. But we realized this would not simulate the actual undersampling that a quick MRI scan would actually go through. And so this sort of Fourier transform, multiplying mask, and then, you know, inverse Fourier transform, that's sort of what we realized we're going to have to do just to simulate what it would be like if an actual MRI image were to generate an MR scan with less data than a normal scan. Aman, did you have anything for this slide?
Yeah, so click that, there's a hyperlink. If you click that. Okay. I guess, I don't know if
yeah, let me exit the presentation.
Yeah, there should be a hyperlink that I threw in there, but I can probably pull that up.
I think I got it.
You got it?
Oh,
okay.
Wait, never mind.
Okay, we'll come back to that slide. It's not super important. It's
Okay.
just kind of showing the slices, but we'll come back to that at the end.
Yeah, no worries. Okay. Just moving on. So based on what we said, this is how we generated our undersample data set. So you can see over here we have the ground truth images, which were the NII files that we mentioned from MRNet, or the MIRRAI dataset, which is another dataset. And then we did the undersampling by multiplying the mask and doing the inverse Fourier transform. And now for every perfectly scanned image, we have a corresponding undersampled image, which we then use as a pair when training the GAN. And so essentially we would be passing in the undersampled image into the generator to reconstruct the image into a higher quality image, which we would then compare to the ground truth and pass into the discriminator. But we'll go into that more detail in future slides.
Yeah, so that's kind of building off of what Nikhil was talking about. So let me kind of go into the specifics of the architecture. So we have a generator and a discriminator, and the architecture is kind of what you can see over here. So with our generator, it's based on a UNet. So we have several encoders, and then we have corresponding decoders that are linked by these residual links. And then all the encoders are going to have convolutional layers. So that's what you see on the left. And these are pretty much just reducing the feature space. And then into our latent vector. And then finally, when we have the latent vector, we reproduce the image through the decoders, and we apply inverse convolutional transpose layers, which do the opposite of convolutions. And then at the very bottom, as you can see, these RRDBs, that stands for residual and residual dense blocks. And pretty much we have those to help with two things. First of all, to just make our network even deeper. And then another thing that these help with is just avoiding the vanishing gradient problem. And then we also have these skip connections, as you can see, and that just helps with making these identity mappings easier. And then After each convolutional and transposed convolutional layer, we have a batch normalization followed with a ReLU activation. So that's on the generator side. And then for the discriminator side, it's pretty much just a CNN with 11 layers. And each convolution is followed by a batch norm and then ReLU. And then as the discriminator does, it's going to give the probability of being real or fake. So we have a 10H activation, and it's just an average score that's going to classify the input as real or fake.
Yeah, that's pretty good. One thing I did want to add that we're going to be going into detail in our paper is like these RRDB units are kind of new when it comes to GANs. Like previous research in super resolution has shown like the efficiency of RRDBs, or the effectiveness rather. And as Aman said, it deepens our network, and the purpose of deepening our network is to be able to map more complex functions with our generator, which is more promising for our results. And then going into the specifications of like our research, we decided to use a conditional GAN, condition on the k-space. And just as Aman said, we're passing these undersampled images into the generator to reconstruct them into fully, into higher, like higher quality images. And then we use MAE loss, or I think we actually also used something called a Wasserstein loss function, which is, I think, something that we were looking into to improve the stability of our GAN during training. And then we also implemented weight clipping to prevent exploding gradient. And then we used a batch size of 32 with 300 epochs. And I can actually, I have this open on my computer, but you can see this is AWS, Amazon SageMaker Studio. And initially, like, we tried running this on our computer, except we didn't get like amazing results because the compute power was just not there. We tried running this on CUDA, but I don't think we really optimized it for the GPUs as much as we should have. I don't know, we were sort of experimenting with that. But we tried running it in SageMaker, and we got some pretty good results. So you can see over here, we load the MRNet dataset over here. We can specify the number of files to load, the number of slices to load. This is the mask that we use to multiply with the k-space to undersample it. And then we do the inverse Fourier transform over here. And then down here, you can sort of plot an example of what a ground truth normal image from the dataset looks like, and then an undersampled image. And then in our model over here, this is just basically all the layers of our generator and discriminator, or this is our generator. Up there was our discriminator. And then you can sort of see right here, it's doing the training with all the epochs and the batches. And then we tested it out and plotted an example. This is sort of the ground truth. This is an undersampled image, and this was like what an example reconstruction would look like, which would be the output of our generator. And this is only with 9 epochs and 100 samples for the training data set and 10 samples for the test data set. And so if we were to like continue this, we would probably like dive deeper into this, but we'll talk about that a bit later. And then as I showed you, like the model is implemented with Keras and TensorFlow. And yeah, that's pretty much the specifications of our research.
So I just wanted to add one more thing to Nikhil's slide. So one thing that is pretty interesting actually, that I've never really seen before, but pretty much we noticed that in the way the paper implemented it is for every time you train the generator, the paper was also saying that they trained the discriminator three times for every train of the generator. So I was kind of confused why they were doing that, but I realized that that's kind of like adding sub epochs to each epoch. So it kind of makes it as if you train it for like 100 epochs, it's almost equivalent of training it to 300 epochs. So I'm still kind of looking into understanding that fully, but I thought that was kind of interesting how for each like epoch they were training the discriminator 3 times. So
yeah, I think it's interesting how they found like the 1-to-3 ratio. That was kind of I'm curious if that's like another hyperparameter that could be used for experimentation.
yeah. Okay, so pretty much over here, we're just getting into the results. So overall, we see that our GAN loss is pretty high. And I think this is, we're not really sure why this is right now. This is just something like we should be seeing the pattern where throughout every epoch, our loss is decreasing. So we see that with these other metrics like our MAE, with the discriminator loss and with the generator loss, but the overall GAN loss is still kind of high. So yeah, this is something we weren't really able to look into, but we hope we can in the future. So, oh wait, this is your slide. Yeah.
Oh, okay. Yeah, so this is just sort of an animation that we try to put together that shows you like across each epoch, the model is like getting better at generating images that look closer and closer to the ground truth. Like again, we were hoping for more promising results, but I think since like the MRI images are just like super, they're not like 28 by 28 pixels. These are like actual MRI images, and you need compute power for these sort of things. So I feel like if you're trying to use this in industry, for example, I think you would use a pre-trained model that has gone through a lot of compute rather than just training this on our laptop. But yeah, the shortest sort of shows you like how the model is improving over time.
Cool. All right, so now let's talk about kind of what we did in addition to the research paper. So one thing that we incorporated was that to all of our undersampled images, we wanted to add varying levels of noise. So the research paper just added like one ratio of noise to the undersampled images, but we added several sets. So 10%, 20%, and no noise at all. So pretty much we just generated the noise from a random distribution and then added the noise to the case-based itself before we did the inverse Fourier transformation. So that was one piece of functionality. And then the second piece was kind of what Nikhil was showing on the previous slide. We just created this metric where we could see that for each epoch of training, how our reconstructed images are, like how the GAN is pretty much learning how to reconstruct the images. So that GIF you saw on the previous slide, that was showing for each epoch, how is the image getting better and better.
Also, just like things that we realized while doing the research, there are potential next steps that we could take beyond just like implementing the paper and adding the functionality that Aman described. We really wanted to get GPU like compute working, because I feel like we were on the verge of creating some of the most like realistic reconstructions with the SageMaker, but I think if we were to continue this project, you know, we would definitely like get that down. And then also like using different masks. We showed you like I can show you. We used this one mask basically throughout our whole research, and that was sure a random distribution, but just experimenting with different types of masks and stuff, that would be really interesting. And then improving the similarity metrics compared to the generated images, just to like gauge how accurate our reconstruction was compared to the ground truth. I think that was really important to experiment with. And then just test with more data sets. I sort of transitioned from that first data set, which was MIRRAI, to the MRNet data set in the middle of the semester. But just like looking into more data sets with these NII GZ files, that'd be more interesting.
Yeah, and I think kind of building off of the similarity metric, I think that's like kind of what we realized is the hardest part about like image processing in general. It's hard to like compare images. Like how do you actually compare like how the reconstruction is to the ground truth? How do you know which areas are more important? Because like, for example, the areas where the muscle are more important to focus on than the black pixel areas. So I think adding some kind of a similarity metric that adds weight to areas of interest, like where muscles are, where certain tissues of interest are, is definitely like a direction we want to go in as well. But yeah, do you guys have any questions?
Yeah, this Gustavo. Can you go back to the architecture of the network where you show the GAN and the unit? Okay, very nice. Okay, so let's see. So you Age is the generator architecture. So the input there will be the low resolution image. Is that right?
Yeah,
And then
the
the output is
undersampled
going to be
image.
the high resolution image.
Yeah.
Okay.
Correct.
And then,
Actually the input is, it's not just one image. It's actually, so we actually use the CGAN architecture. So it's going to be the undersampled image conditioned on the ground truth. So it's going to be those two images concatenated as our input.
okay.
Yeah.
And then okay, and then the output, what would be the output then?
The full reconstruction. Yeah.
Okay, the full reconstruction. Okay, and then you have the discriminator. Can you explain the discriminator? What is the input that you have in here?
So
Yeah. So go ahead, Aman.
Yeah, so discriminator is pretty much just going to be the reconstructed image, and we are going to apply convolutions to it and try to see, is this image fake or real? So it's just going to assign a probability, real or fake, and that's how it's going to learn how to pretty much discriminate the images.
Yeah.
Okay, and then when you once that you let's see. So once that you train, then your input would be what? Okay, once that you have trained and then you want to use your network to reconstruct, then what do? You just put, yeah, go ahead.
So basically, in industry, you would have a typical MRI machine, but instead of having it for multiple hours, you can train it or just run it for, let's say, I don't know, 15, 30 minutes. And that's going to give you less data, which then you can just pass in to the generator to get your image. You just need to pass into the generator.
Okay, and then you need to pass as input two images, right? In that case would be the low resolution images, is that right? And then the output would be the high resolution?
Yeah, correct.
Okay, so you repeat the low resolution image twice then?
Aman, for if you're actually running this in production, what would be your condition like label?
Yeah, that's what like me and Nikhil were literally talking about this before the presentation. Yeah, I'm honestly not sure what the condition would be.
But anyway, when you let's see, when you obtain the error, how are you computing the error? Okay, so you take the reconstructed image and then compare it to the ground truth and then pixel by pixel, is that right?
Mm-hmm. Yeah, and we have a loss that measures it, yeah.
Okay, so it's like a quadratic, the square of the error or something like that?
Yeah, I think mean squared error or some like Weiser-Seen loss or something that's similar. Yeah.
Okay, and then let me think. The other thing is that you are using 2D images, or actually you are using the sequence of MRI images.
Yeah. So
when you do a reconstruction.
For this project, I think we're only using 2D images, but
Okay.
sort of the next step is to use a different architecture like VNet or U squared 3D net, which basically you can pass a volume of slices instead of just one slice, and that would be just much better for industry,
Okay.
I think.
Okay, and then, okay, so if you are using 2D images, these are just regular convolutional networks, right, in 2D images. If you
Yeah.
want to
Right.
extend this to a volume, then the convolutional network, instead of using a regular 2D, then it has to be like a 3D convolutional, right? Something like
Yeah.
that.
Yeah. The 3D
Okay,
convolutions.
interesting. And how do you call that one you said?
It's called
VNet.
VNet, is a VNet? Okay,
Yeah.
okay. Yeah, well, very, very nice. And you guys were using AWS for training of this?
Yeah, we were using SageMaker for a bit of it. I do want to use more because we got really good compute with this. So you can see over here, we were using this ML G4DN X large, which had 4 vCPUs plus 16
Okay,
gigs of
and what is that?
memory.
In Amazon or where is?
Yeah, this is Amazon SageMaker.
Okay, and it's free? It's free, or what did you do to get access to it?
So I think like I ran this quite a lot, and I think it actually charged me like $7, which I have to pay, but I think it's totally fine. I mean, I'm not.
Yeah, well,
Gonna...
$7 for this processing, I don't think that is much. I was expecting
exactly.
more money. Okay, but yeah, be careful with those bills.
Yeah,
Yeah,
for sure.
okay.
Amazon once charged me like $50 for doing almost nothing on one of their servers.
Wow.
Yeah, okay.
Yeah, our 307 server got hacked this semester. Somebody ran some script on it, and apparently we had to pay $30 for it.
Well, it's not. Yeah.
Oh.
Well, he's going for lunch with friends, right? So.
Yeah.
Yeah. Okay. Great. Excellent. Well, congratulations. Thank you very much. Very good job.
Thank you. Yeah.
Okay.
Thank you.
Great. Yeah. By the way, Max, is there a way that we can put these presentations in a Google Drive? Have you guys put that presentation in a Google Drive, Nikhil and Aman, or no?
Yeah, we have everything compiled on GitHub actually. So
Okay.
the code and the presentation.
Okay. Can you put? Did you share the Google Drive with them, Max?
I think so, but let me make sure. I'll make a document during the next presentation here.
Okay. Yeah. The other thing did we ask the NIP students to put their things in Google Docs?
So we did. I'm not sure if many of them actually did it.
Okay.
But
yeah, could we do? Could you check? Could you check? And if they didn't, then ask them to do it, and tell them if they don't do it, then we will not pass the grade or something like that. Or we may not pass the grade. Tell them.
Okay.
So as a requirement, you can say as a requirement for grading, yeah, we need you to put this presentation in Google Docs, right? Something like that. Okay. Yeah. For you guys, okay, you know that is not necessarily true, but yeah, it would be nice to have your presentation there in Google Docs.
Yeah, we'll
do.
Back up for this one before the end, before we're even done here.
Yeah, thank you. Great. Yeah, very good job. Thank you very much.
Thank you.
Thank you.
All right. Who wants next?
I can go.
Cool. Go right ahead.
All right.